For this last practice problem, we want to find the x-coordinates of the local minima for this polynomial function. So we have a choice here. We could use the first derivative test or the second derivative test. Since this is in the second derivative test section, that's what I'm going to use to solve this. So we're going to use the second derivative test. So the second derivative test says that we want to find the critical values for this function. And if we put those into the second derivative and we get a positive value, then we have a local minimum. And if we put a critical value into the second derivative and we get a negative value, then we have a local max. So let's find the first derivative so that we can find our critical values. We have 4x cubed minus 8x, and then we're going to set this equal to 0. There's no place that this is undefined, so I don't have to worry about that. And let's factor out of 4x, and we'll have x squared minus 2. And I can keep factoring that as x minus the square root of 2 and x plus square root of 2. And that will give me critical values at x equal to 0 and plus or minus the square root of 2. Now here's where the second derivative test kind of branches off from the first derivative test. So we're going to find the second derivative. So the second derivative is going to be 12x squared minus 8. And now we're going to put each critical value into that second derivative. So actually, let's move that up here. And we are going to put each of our critical values into that function. So let's find q double prime of 0, which will be 12 times 0 squared minus 8, and that is a negative value, which means at 0 we have a local maximum. So we've got a local max at x equal to 0. Then let's try the negative square root of 2. That's going to be 12 times negative square root of 2 squared minus 8. And this is 12 times 2 minus 8. We don't care what that value is, we just know it's positive. You can go ahead and find it if you want to. But because we have a positive value, we know that we have a local minimum at x equal to negative square root of 2. And then finally, we will look at positive square root of 2. And because of the nature of this function, you can see that we're going to get the same value as we did for the negative square root of 2. So it's going to be positive, which means we have another local minimum at x equal to positive square root of 2. So we have two local minima here at x equal to negative square root of 2 and x equal to positive square root of 2.